Yeah guys, Mr. Bennett here, and today I'm going to be looking at a fission reaction and the process behind how that works. So hopefully this will make sense for you, and it's definitely one of the applications that you do need to know. Alright, so really important that you understand the process. Now, the first thing is what actually happens in a fission reaction. We have a neutron that moves into a uranium-235. Now we use uranium-235 because that does, we know, basically spontaneously decay when you introduce a neutron. Now what you'll get is, you'll get a particle A, you'll get particle B, and then you'll get 3 neutrons being produced. That's a typical reaction. It's not the only reaction that you can actually get. So typically it might be that particle A is barium, particle B is krypton, and then you get 3 neutrons. And the most important part, I suppose, of this is because you're breaking up the nucleus, you're getting the binding energy, and that is emitted in terms of gamma radiation, when you're doing that. Alright, so the first step when we go through the process of nuclear fission, step number 1 that you must do is you must enrich your uranium. Okay, so when we enrich our uranium, we know that uranium-235 easily fissions, so where uranium-238 doesn't. So what we need to do is we need to enrich uranium-238 with up to about 5% of uranium-235. Okay, so that's what basically happens. You don't need to know how that actually works, but we know we produce what they call fuel rods, okay, that will actually fission. So that's the first step. The second step is you have to have a thing called a moderator. Right? The moderator is an important part of the fission process. So the moderator has a mass which is about similar to that of a neutron. Okay, we have to slow the neutron down. Alright, so it has to be maybe a little bit heavier than a neutron. The typical sort of moderator we might use is deuterium water, heavy water. Okay, so instead of using a hydrogen, we use a isotope of hydrogen, deuterium, and we make heavy water out of that. The properties of the moderator is the moderator cannot absorb the neutron. Right, we don't want that to happen. We want it to slow it down via a series of collisions. Now I think the best way for me to remember this is it's a bit like the neutron going through a crowd. Okay, if you've got a really big crowd, if the neutron's trying to move through quickly, it's going to hit the different people in the crowd and it's going to slow it down a little bit. Right? So if you think about if you ran out on a 100-meter track, and then you were running through a crowd, you're going to get slowed down because you're actually making collisions with the other people. Alright, so that's what happens in the heavy water. The neutron is basically getting slowed down because it's hitting the heavy water and it's slowing it down. If it wasn't slowed down, it's a bit like something hitting a bowling, like a marble hitting a bowling ball. What's going to happen is it's just going to rebound off the uranium-235 atom, so therefore it won't be encapsulated into the nucleus. Alright. Step 3 in the process is the neutron is captured. Alright, so in step 3 of the process, we capture the neutron. Alright, so in here, what's going on is the neutron goes into the 235. This is a very big atom anyway, and so therefore what happens is the atom gets elongated. Right, because we now have that strong nuclear force is not as strong as the coulombic forces because the atom's too big, so we get those things. So what actually happens is it gets elongated, and we know that the electrostatic force is now taking over, and then that gets split into 2 different atoms, right? And then we get our 3 neutrons being produced as well and emitted. Alright, so that's what's basically happening in that next stage of the fission process. Right, we must have, for fission to occur, we must have critical mass. The critical mass is a certain amount of mass that will allow a sustained nuclear reaction to occur. Alright, so we must have that critical mass. That's actually an important part of it. Then what we want to do is we want to have a sustained controlled reaction. If we don't have a sustained controlled reaction, then we have basically a nuclear bomb. And we don't want that to actually happen. So it has to be sustained and has to be controlled reaction. Now, we'll talk about how that actually works in the nuclear reactor itself, but you use control rods in order to absorb some of the neutrons. Because remember, every reaction, one neutron produces 3 neutrons. What we want to have in our reaction is 1 neutron, then instigates a reaction, producing 1 neutron to instigate another reaction, producing 1 neutron. So once we get up to our critical mass and we get a controlled reaction going, what we want to do is we want to control the number of neutrons that are causing fission reactions. If we can do that, then we can actually control the amount of reactions that are occurring. So that's what we do. We use control rods, which are generally made of cadmium or boron, okay, and they basically absorb neutrons, those 2 elements. All right, so if we don't have that, then what we have is the idea of this uncontrolled chain reaction, which is a nuclear bomb. All right, so therefore, if you're thinking about, the 3 neutrons, right, become 3, become 9, become 27, 81, all of a sudden, by the time you get to 50, you're looking at a huge number of neutrons, okay, and that's kaboom stage, all right, and we don't want to have that. We want to have controlled chain reaction in our nuclear reactor. Alright, so we will look at the nuclear reactor and the parts of it, so you can identify how that actually works. Obviously there are different types of nuclear reactors nowadays, but you need to understand the old sort of style one there. Okay, so that's pretty well the fission reaction process. Alright, so if we just recap that very quickly. Alright, so the first thing, we have to have enriched uranium, 5%. Second bit, we have to have this moderator that slows the neutrons down so they can get encapsulated into the uranium-235. And then what happens, we get this massive nucleus, which then becomes elongated because the coulombic forces, or the strong electrostatic forces are overtaking. It splits into its things. We must make sure we have a critical mass so this reaction can occur. And then we need to control that reaction using our control rods. So we have once we get up to a reaction sort of rate that we're happy with, we have 1 neutron producing a reaction and producing another neutron to produce another reaction. If not, then we have a bomb situation. Okay, we'll leave it there and we'll talk about that in class.